First of all, I'd like to thank the organizers for giving me this opportunity to present this work. By looking at the clock, I see that my time is up according to the program. I'll use what you kindly give me. So I'm going to tell you about some peculiarities of interferometry in the quantum Hall effect. Here's the point. And first of all, I'd like to remind you what the quantum Hall effect is. It's observed in two-dimensional layers of electrons subjected to a very strong magnetic field. And what's important for us is that the bulk of the system is insulating. Nothing interesting is going to happen there, at least in this talk. And whatever is going to happen is taking place at the edge. The edge is chiral, at least in the very simplest cases I will consider in this talk. And that means that whatever propagates on the edge, it propagates in one direction but not in the other. The system is composed of electrons. And electrons, they have, well, the charge of electron, and they are fermions, meaning that when I exchange two electrons, I get a minus sign, which gives me some sort of locality, that when I take one electron round the other, I get nothing, I get back to the original state, because it's like I exchange electrons twice and minus 1 squared is 1, so I get to the original state. However, if I'm in the fractional quantum Hall regime, the system also supports fractional quasi-particles. They have charge which is a fraction of the electron charge, and they have some peculiar statistics. When I exchange two quasi-particles, I get a phase, and the sign of the phase depends on whether I exchange them clockwise or counterclockwise. As a result, if I take a quasi-particle round the other, I don't get to the same state, but I get to the same state multiplied by a phase. Formally, the quantum Hall edge, again in the simplest cases, is described by a single bosonic field, which has some commutation relations. Charge density can be expressed through this bosonic field, and that's going to be important in this talk. Electrons and quasi-particles are some exponents of this bosonic field, and one can check that they indeed obey the correct statistic relations. Now, the title also contained the word interferometer, and I'm going to talk about Mach-Zehnder interferometer. So let's consider a quantum Hall system with a hole inside. Then I have not just the outer edge, but I have also the inner edge which propagates in the opposite direction. And what's usually done is one injects some current here and measures what arrives here.
So is it just turbine geometry?
Yes. So if I inject something here, it can travel to D2 in two ways, either like this or like this. And these two paths are going to interfere. And since the system is subjected to magnetic field, then the interference amplitude is going to contain the magnetic flux between those two trajectories. And if I had electrons traveling in my system, I would expect the Aharonov-Bohm effect in the interference current. But since I have fractional quasi-particles traveling in my system, I have to replace the electron charge by the fractional charge, and naively I expect some fractional Aharonov-Bohm effect. However, let's see how to describe the system formally. For that, one needs to introduce tunneling operators. One of them will destroy a quasi-particle at A and create it at B, and the same for CD tunneling junction. There is a problem, however. If one describes the two edges as separate edges, the quasi-particles at the inner edge and at the outer edge, they commute. So there is no proper statistical phase, and as a result, I have non-commutation of these two tunneling operators. And they should commute fundamentally for the simple reason this tunneling process happens far away from this one. So if almost at the same time this quasi-particle tunnels here and then this one tunnels here, it should be the same as this one tunnels first and then this one, because they are far away from each other. No information can reach the other tunneling junction about what's happening in the first one in no time. So that's a problem. And in literature, there are some solutions around this problem. The most simple one is to take the statistical phase into account by hands. So if the inner edge has k quasi-particles and my tunneling quasi-particle effectively it encircles the inner edge, so I have to take into account the statistical phase due to this. I put it into this current expression by hands, and that's it. There is, however, a subtlety. The ohmic contact can only absorb electrons. There are no fractional quasi-particles in usual metals. Therefore, the quasi-particles have to go into the ohmic contact by some packs of several quasi-particles. And therefore, they will have to wait, they will have to spend some time, I will get some average of the individual quasi-particles current, that will be the resulting current. And one can see that the fractional Aharonov-Bohm effect has disappeared, and also the interference visibility, which is the interference amplitude over the constant amplitude. Effective visibility gets reduced by the number of how many quasi-particles should tunnel. Anyway, in this approach I get electron-like Aharonov-Bohm effect due to the ohmic contact absorption properties. There is another solution in literature which says, well, the tunneling operators don't commute. Let's make them commute by introducing additional operators kappa 1 and kappa 2, which take care of the statistics. And then the operators start commuting. And after some calculations, these references, all of them, they get electron-like Aharonov-Bohm effect again, but not a single word about the ohmic contacts. So the two approaches, they get the same result, but for different physical reasons, which is something I believe one has to reconcile. And there is another issue with this second approach, is that these kappa I operators, they commute with quasi-particles, which means they are some additional degrees of freedom not previously present in the edges theory. And no one really says what these degrees of freedom are. However, in the end, one has to face experiment. So whatever theory one uses, one expects to see some electron-like Aharonov-Bohm interference with some non-zero visibility. And recently, the Heiblum's group of Weizmann Institute published the data about Mach-Zehnder interferometry, and they say that visibility goes down around fill-in factor 1, and then for any fractional quantum Hall effect below fill-in factor 1, they see nothing. No fractional Aharonov-Bohm effect, no electron-like Aharonov-Bohm effect, nothing at all. Well, one can say that fine, for some reason this I int is 0 and 1 sees nothing. However, Heiblum's group is famous for measuring noise in such systems. And they measure noise and they show that zero visibility is incompatible with the noise data, which suggests that there is some phase averaging, which means that cosine average is 0, but in the noise and the quadratic incurrent expression, the contribution of interference term is non-zero. That is something none of the theories before explained, and that's what I'm going to do. So, once more, we had the Mach-Zehnder interferometer and the tunneling operators didn't compute. Now remember, when I had one edge, the statistics was taken into account very well. I had no problems. So maybe I can redraw my system like this. Now this is a single edge, and indeed one checks the tunneling operators do commute. However, I've missed dynamics. Before the quasi-particle here went here, now it should divert here. Is there a way to divert quasi-particles from here to there? Yes, there is. it is known that if one takes two quantum Hall edges, brings them closely, there are quasi-particle tunnelings between them. One brings them closer and closer, quasi-particle tunneling becomes stronger and stronger, and eventually the quantum Hall liquid splits into two parts between which only electrons can hop, not quasi-particles. And the opposite also works. If I take two parts, I bring them closer and closer, I make electron tunneling stronger and stronger, eventually they will join. And I will direct whatever is coming here, it will go there and not there. So that's what I'm going to do in my system. I'm going to put strong electron tunneling between these two segments. So I take these two segments, I say my Hamiltonian here is tunneling of electrons from here to there and vice versa. And if the tunneling amplitude goes to infinity, then the cosine argument is locked, and I have this boundary condition, this relation between fields here and here. So I have boundary condition between x and y, which is this, and m is some integer valued operator, and between z and w. The question is, what is m? For that, I remind you that the charge density of the edge is derivative of the field, so the charge of some edge segment is integral of charge density, is difference of the bosonic fields at 2 points. So using this, one can easily show that this M operator is related to the inner edge charge. So essentially it counts the number of quasi-particles at the inner edge. So I have this boundary condition now for Z and W fields, but before I had just continuous transition. Therefore, if I want to express the new operators in terms of old fields, I need to redefine quasi-particle at D by this exponent. And so effectively I've introduced a Klein factor of this form, and one can check that yes, the tunneling operators do commute now. And if one calculates what is the interference contribution when I have k quasi-particles on the inner edge, then yes, I get an additional phase, which is just the same phase I would put in by hands, which is good. And there is an important approach, there is an important difference of this approach from the second approach, which introduces ad hoc Klein factors. Here I have charge, and I have some charge and energy associated to putting charge onto the inner edge. And that is going to have a physical consequence. So I remind you, the effect of ohmic contacts was that I put statistical phase, and I had the first quasi-particle came, it felt one statistical phase, the next one came, it felt another statistical phase, and eventually several quasi-particles came, and they went to the ohmic contact, but all of them, they felt different statistical phases. But now I can imagine the following scenario. The first quasi-particle comes and waits at the ohmic contact while the others arrive. Then the second quasi-particle comes, but before it comes, because of temperature fluctuation, some quasi-particle jumps onto the inner edge. Then the second quasi-particle comes, it feels not the statistical phase it should have felt otherwise. Then, after it came and waits at the ohmic contact, that thermal fluctuation goes back, and I have the second quasi-particle felt not the phase it was supposed to feel. So if one puts that formally, I have some charge fluctuation at the inner edge, and the kth quasi-particle that comes, it feels not the phase it's supposed to feel, but some other, and the fluctuations are governed by temperature, so I get some current averaging. And obviously, at infinite temperature, the cosine will get averaged to 0, I will get no interference at all. At 0 temperature, I will get the result of solution 1. And at finite temperature, I will get something in between, so in principle, that can explain the experimental observations. So let's plug in some realistic numbers. I plug the edge length and the velocity of the edge, which are reasonable for the experiments of high blue, and I calculate for u equal 1/3 the average value of this exponent. And you see, at high temperatures it goes to 0, at low temperatures it goes to 1, and the experiments were performed between 10 and 15 millikelvin. So you see the visibility is reduced by this additional factor, and this factor is less than 1/10, which results that the effective visibility that takes into account the ohmic contact properties is less than 1,000th, less than 0.1%, which is effectively unobservable. And one can, which pretty nicely explains the data for the current. And one can ask the question, what should be the temperature to observe nice visibility of order 1? And one can see that this is about 1 millikelvin. So just 9 millikelvin below the experiments. But 9 millikelvin is one order here, one order of magnitude, and that's going to be quite challenging, unfortunately. So in conclusion, I've proposed a new approach to the Klein factors that unifies previously used approaches. And this approach gives additional temperature dependence of the interference in Mach-Zehnder interferometer that explains the absence of interference current in the experiments. However, I have not calculated the noise, so the noise still remains to be understood. What I proposed is related to the simplest Laughlin fill-in fractions, but in principle it is generalizable to other fill-in factors. And finally, this scenario cannot explain the absence of interference at mu equal 1. Because if you see, when I have fractional quantum Hall, these fluctuations are fractional parts of E, and the exponent fluctuates indeed. But when I have integer quantum Hall, this delta Q is E or 2E or 3E, it's always 1, no visibility reduction takes place. So possibly other mechanisms come into play at mu equal 1. I thank you for your attention, and I'd be glad to answer your questions.
Can you explain the meaning of the capacitance? Because it depends on the parameter of the length of the inner edge, but it is like, it depends on how you effectively glued your systems, and it could be like, it looks like arbitrary parameter that
if you plug in edge theory, you get this capacitance, exactly the expression I put, and it depends on the inner edge length and the propagation velocity, which is some energy parameter of the edge. And it does not depend on the way how I glued my system. It depends, okay, my resulting glued system has some edge and it has some length. And that's the length that enters there. So what I actually did, I took a picture of the interferometer from the experimental paper and measured the length with a ruler. And multiplied by the scale, obviously.
So which length should enter this capacitance when you will have not these perfect circles, but they will be different in different places?
Yeah, I should take the length in parts.
Ah, okay.
I hope my edge is not fractal.
Okay. Question is, you said that, okay, these statement experiments are just outside the threshold, and you mentioned on the temperature side of the question, but there are many other parameters, for example, length. So is there any way to prove like that?
Yes, indeed. There are two parameters, length and the propagation velocity. With length, there is a problem. One can reduce length, but then one risks entering Coulomb blockade regime, when the transport is not governed by tunneling probabilities, but by the Coulomb energy of the inner edge. And that's not something one wants to have. And there is edge velocity. And frankly speaking, that's the only parameter I didn't take exactly from the experimental data, because the edge velocity is usually determined by interference pattern, and they see no interference, so they know nothing about the edge velocity, so I had to take velocity at mu equal 1 and make some reasonable estimates. Yes, the velocity can be different in principle, but you see the velocity enters pretty much like the temperature. So if I need to reduce temperature 10 times, increasing velocity 10 times would work fine, but that's also challenging because one has to have very nice control over the sample trapping potential. Thank you. Last question.
Okay. Did I understand correctly that at least at zero temperatures you always should have electron-like Aronoff-Bohm effect?
Yes, that's what I would expect because of the ohmic contact properties.
And if you increase temperature, this quasi-particles with fractional phases sort of behave independently from each other.
Well, they do behave independently in each tunnel.
In statistical sense.
But I have to accumulate several quasi-particles, and if the temperature is low, they behave not independently, and I have electron-like Aronoff-Bohm. But if the temperature is high, I get interference destroyed for every single quasi-particle tunnel.
But this means exactly that these quasi-particles, due to thermal fluctuation, become to behave independently from each other. They are statistically independent. And the related comment about Klein factors. You mentioned that it is connected with some additional degrees of freedom. Like
in the standard approach in the literature, in my approach, it's perfectly expressed through the electric charge.
I mean, could it be that when you consider the electron operators which do not pick additional phase, then so they commute, and that means that, as you said, the tunneling processes A, B, and C, D are independent from each other. And could it be that because so you have a factorization of your tunneling term on Klein factors and let's say electron density, psi, dark psi.
For the electrons, the Klein factor I introduced would be trivial.
And could it be that tunneling is a slow process in time?
Yes, it is.
And if you take a big time scale then they are independent. So I mean, could it be that in Klein factors there are modes which
some high energy?
Yeah.
Well, I wouldn't believe that. Well, in principle, it could be the case, but I doubt that. And that's not the case in my approach, anyway.
Let's continue this after. Yeah, so let's thank Kyrylo.